Right, I'm going to say that last bit again because I don't think it was particularly clear. The point was that the centre of G is the set of all those elements in G such that for all G in G, such that every other element commutes with it. Okay, that's in a way the easiest way of thinking about it. But we can rephrase this as being all those elements such that, given any other element G, what this is saying here is that A is in the centralizer of G. A is in the centralizer of G. So you go around saying, okay, is A in every centralizer of every element? And if it is, then it's in the center, and that's precisely all the centers. So what that's saying is it's the intersection over all elements of G of the centralizers. So this, each of these is a group, right? Each of these is a group. And we know that because it's the stabilizer of something in a group action, so it's got to be a group. And we know that the intersection of groups is a group. So this immediately tells us that the center is a group. But it's better than a group because it's actually a normal subgroup of G. So now we can sit down. If you didn't understand that, don't worry about it because you don't actually need it. We're going to sit down and prove directly that this is a normal subgroup of the group. Right, proposition 6.2.7 that ZG is a normal subgroup of G. Okay, so that, remember, means is a normal subgroup. So first of all, let's prove that it's a subgroup. First of all, let's show it's a subgroup. So we'd better show that it's closed under multiplication. So suppose that we have A and B in the center. What does that mean? It means that GA, for all G in G, GA, G minus 1 equals A, and GB, G minus 1 equals B. That's what it means to be in the center. Then we need to show that AB is in the center, i.e. that G, AB, G minus 1 equals AB for all G in G. But look, now we can do a little trick. We can do a moment of futility in the middle there. GAB G minus 1 equals GA G minus 1 GB G minus 1. So we have a little moment of futility here, which is why that's equal to that. But now, because A is central, we know that that's equal to A, and because B is central, we know that that's equal to B. So we have shown that AB is really in the center. So we've done that. We know clearly that E is in the center. We know that E is in the center. And also, we know that if A is in the center, then A inverse is in the center. If A is in the center, then A inverse is in the center. Because, well, let's look at G A inverse, G inverse. Why is that in the center? It's in the center because, oh no, why is it in the center? I'm I'm going to pause for a second. Okay, phew, I'm back. What we have to show, we need to show that GA inverse G inverse is A inverse, but we know that's true, right? Because GA G inverse equals A, so if we take the inverse of that, it's just G, so inverse is, we just invert this and write it backwards, right, is G A inverse G inverse. So that really is true. So that really is true, so A inverse is in the center. Phew! Right, so it's a subgroup, now we need to show that it's normal. We show it's normal. So what do we need to show? We need to show that for all A in the center and G in G, that GA G inverse is also in the center. That's the definition of being a normal subgroup, right? But this is just obviously true because GA G inverse equals A, because A is in the center. That's exactly what it means to be in the center. And A certainly is in there. So we have shown that if you take any element of the center and conjugate it, you stay in the same place, so you certainly stay in the center. So indeed, the center is a normal subgroup of G. So finally, I want to give some examples of centers. Examples of centers. First of all, one, if G is abelian, then the center is the entire group. Because the center is every element that commutes with everything. And in an abelian group, everything commutes with everything. So the center is the whole thing. The center of D4, now we've actually seen this in the previous lecture because we found all the conjugacy classes in D4 and we discovered which ones were sitting in little conjugacy classes all by themselves. Now if you're in the center, you commute with everything, which means that no matter how much anybody conjugates you, you don't move. So what that means is that you're in the center. So the center of D4 was all those elements that were in conjugacy classes all by themselves. All elements in their own conjugacy classes, and we saw that those were E and A squared, which was rotation by pi. However, if we do this to D3, we discover that only E is in a conjugacy class all by itself. So one thing that this tells us is that we can look at the class equation and find out how big the center is, because it consists of all those ones. If there's a 1, that was because an element was in a conjugacy class all by itself, so the ones tell us what the center is. So NB, the ones in the class equation tell us how big, tell us which, how many elements are in the center, how big the center is. So we'll do that again at the beginning of the next lecture.